thank you very much. Take it away. Thank you. So this is actually a 1-hour talk for my Caroline Herschel Prize. Obviously, we don't have that kind of time, so it will be condensed, and some of the bits will be skipped. If you want to see some of the fun videos that I'm going to skip today, you can come see me at the end, and I'll do my best to give you a show. So my timeline is going to be a lot less advanced than Rachel's. I did my integrated masters at the University of Sheffield, where I moved when I was 18 from France. That's where the accent comes from. I was in the Canary Islands for a year during my master's to work at one of the telescopes, and then I moved back to Sheffield to do my PhD. Then I moved to New Zealand to do my first postdoc, where I studied stellar genealogy. I did supernovae and other kinds of explosions beforehand. And then I had a very difficult time finding money. And then eventually I got my Schmidt AI and Science Fellowship. And the reason that I point this out, how difficult it was for me to get money, is because it can take time, and then you can get prizes and things. So don't despair, keep going. So there will be loads of pictures in this presentation that look really pretty. They will either be from actual telescopes or from artist impressions. Nothing was AI generated. It's hard to tell these days, so I want to tell you. Right, so I'm going to start the timer. And then there we go. So to do astronomy, you don't need fancy equipment. People successfully sailed the Pacific with nothing but their eyes and their knowledge of the stars. But new technology can herald new discovery. So the advent of the telescope allowed Galileo to find the Galilean moons. The advent of photography in the 19th century allowed sky surveys to begin. And in the mid-20th century, we had semiconductors, which allow people to control the flow of electricity on a really small scale. That's what turns computers from things that take up a whole room to computers that fit on your lap. And that's also what allows you to make the digital camera, which is very convenient. Another convenient thing from the 20th century is rocketry, because rocketry means you can put your telescopes out into space. And the reason you want to do this for some of your telescopes is that the atmosphere is a big, beautiful blanket that shields you from some of the harshest radiation on Earth, in the cosmos. But it also shields you from some of the most beautiful colors of the universe, some that you really need to see if you want to do cool astronomy. To exemplify this, I'm going to show you something you might have seen before, the Hubble Deep Field. This is an image taken by the Hubble Space Telescope. This is actually a very small portion of that image, only 10 times the size of the full picture. And the full picture is only 10 times smaller than the moon in the patch of sky that looks completely empty. And yet, as you can see, we have hundreds of galaxies. In this picture, every single dot is pretty much a galaxy. This blob, a galaxy, this blob, a galaxy, this blob, a galaxy. That was very surprising. Astronomers didn't expect that to happen. Some people didn't want the Hubble Deep Field to happen. But it's been so successful that we've been doing these deep fields over and over again. And the James Webb Telescope, when it went up to space, did it as well. Now, the reason that I'm showing you these pictures is not because I use them, because I don't. But so I have an excuse to show you some of the cooler science that we've got out there, and so that I can really impress upon you the fact that the history of discovery in astronomy is the story of people partnering with new technologies. That's how you go further in science. You partner with the new bit of tech. And that's the theme I want to explore with you today. So, my job is very cool because I get to travel the world. Last year, I went to Chile at another observatory, and I got to work with this beautiful tin can, which we call the New Technology Telescope. Now, I was there for only 3 days trying to observe the sky. The problem is, you might notice a lot of clouds. And that's not ideal if you're an optical astronomer, you can't see the sky. Now, fortunately, the clouds were briefly swept away by incredibly strong winds that meant I could not do my job, and I had plenty of time on my hands to take pictures. So I took this picture with that phone that is sitting on that table. Here you can see the Milky Way, and you can see hundreds, thousands of stars. Here is another beautiful picture of the Milky Way taken by someone at ESO. Here you can even see colors. This is the center of our galaxy over here, and the clouds that you can see are not clouds in the sky, they're clouds in the galaxy itself, dust and cold gas. Now, you might know, if you've been to a dark sky reserve, that the night sky does not look like this to your eyes. It never looks that beautiful. It looks very impressive, but you can't see that many stars. That's because your eyes can't take pictures for 30 seconds or 5 minutes at a time. In a dark sky reserve, you might be able to see a few thousand stars at most. A telescope like the ones that we use, they can see 1 billion stars. So the sky is really big, is the conclusion, but the sky is not only big in its expanse, it's also doing a lot of things. It's ever changing. We've got things like Orion, the shoulder of Orion, Betelgeuse, that's its light. Over time, you can see it's extremely variable. There's other things going on in the night sky closer to home, like near-Earth asteroids, or a beautiful comet. This near-Earth asteroid got whacked by DART, which is a spaceship. Yes, we launched a spaceship at a comet. At a moonlet. You can look that up later. And Atlas, the telescope that I work with, captured the impact. But there's also the kind of stuff that I care about, which is the really rare stellar explosions that we can see from really distant galaxies. Now, this slide is very overwhelming, and today we're not going to talk so much about that bit of astronomy, but what I want to focus on here are some of the timescales that I've written down. So days, weeks, minutes, hours, days. Those are the timescales on which these objects change significantly. These are the timescales on which we want to take a new picture so we can study them and understand them. So that means that if we want to understand these objects, we have to survey the sky over and over and over again. We have to do our sky surveys not just in space, but in time. And that's the kind of technology we've only had in the 21st century. Sky surveys like Atlas have allowed us to do this. There's other sky surveys, but this one is my favorite because they pay my bills. Atlas is the Asteroid Terrestrial Impact Last Alert System. It's primarily funded by the NSF for planetary defense, so finding and tracking near-Earth asteroids so we don't have the same fate as the dinosaurs. Dining with dinosaurs, never mind. But to do this, it's got a really cool setup. It's not necessarily very big. Each unit is about 50 centimeters, but there's a few of them. We've got 2 in Hawaii, 1 in Chile, 1 in South Africa. And that gives us a 360 view of the sky. Like I said, 360 view is not enough. We also need the cadence. We need to look at the sky over and over and over again. So to do this, Atlas has a really large field of view. This is a slightly overwhelming dashboard, but I will have you focus on these blobs. These are the last images captured by Atlas. And I'm too small to reach. Oh, no, never mind. The reason I want the mouse to work a little bit is because I want to try and draw the size of the moon on this picture. So the moon is about, no, that's not going to work. This is big, about this big. Cast your mind back to the pictures I showed you from Hubble earlier. Those were 100 times smaller than the moon. The moon could fit 50 times in each of these pictures. So we can take pictures of the night sky and go back to the same spot every 1 to 2 days. So we've got a cadence of 1 to 2 days with Atlas, which is really useful to find and track near-Earth asteroids, but it's also very convenient to find things that go bang. Now, this is the part of the talk that we're going to run through really, really quickly. Here are some of the things that go bang. Supernovae. Star dies and then makes a lot of iron that then ends up in your blood. And occasionally, these are also used to track the expansion of the universe. We've got other kinds of supernovae that go bang and then create a bunch of intermediate mass elements like the oxygen in your lungs. They also make neutron stars. And yes, this is a real image. That's not an artist's impression. That's the neutron star you can see. These neutron stars can then go on and explode again in what we call kilonovae. That's what happens when 2 neutron stars hug a little bit too tight and explode in the process. Pictures, pictures, pictures. And these make some of the rarest elements that we find on Earth, like platinum, gold, and the rare earth elements that make our phones work. The other kind of transient I mentioned in this talk is the tidal disruption event, which is where the hungry black holes come in, because here we've got a black hole, whoop, in the center there. This is a simulation, and we've got a star that had a very unfortunate spaghettification event. It got a little too close and got completely shredded, and that causes a big flash of light. And the reason this is super useful is because it basically makes, oh, please work, the black hole glow. This allows you to measure the mass and the spin of the black hole, which is convenient because black holes are very difficult to study. You can't make them in the lab and you can't see them most of the time. So tidal disruption events, very useful. Just with these 3 examples of transients, we can touch on many different corners of astrophysics and how we understand the universe, the origin of the elements that we're made of, the expansion of the universe, that's dark matter, dark energy, probing the really difficult physics of compact objects like black holes and neutron stars. But in order to actually study these things, we first need to find these transients. So we have to spot the difference with the universe. We've got to play a little game. Now, slight change of pace, we're going to talk more about AI before we go back to the astronomy. Can you spot the difference between these 2 images? These are portions of the Milky Way picture I took with my phone that I showed you very briefly at the start. Now, you might notice that this picture is blurrier than this one. You can even see the pixels in this picture. But that's very surprising because these are literally from the same picture, but this is the RAW and this is the JPEG. Now, if you know what a JPEG is, you'll be like, this is weird. The JPEG is a file format that is a compressed version of the raw image. There is less information in the JPEG because it's lossy. So why does it look like it has more pixels? That's because my phone is not a traditional camera, you see. My phone is smart. It has software. It has magic maths that can make more pixels. It has generative AI. So what is AI? We're not going to go into that too much because there's a long history and it's a bit of a contentious point. But for most intents and purposes in life in general, but especially in these kinds of talks, AI is machine learning. And machine learning is statistics. But it just sounds cooler to say we're going to do AI than statistics. So how do you teach a machine to do a task with statistics? Well, you're going to learn a function, a mathematical function. In this talk, there's going to be no maths at all. So we're going to use an analogy for the mathematical function. A mathematical function is a little bit like a DJ deck. Now, you don't need to know how they work. I certainly don't, but I understand the concept. You put music on one end, you turn the knobs and dials, and a different kind of beat comes out, right? It's the same with a function. You put something in, turn the knobs and dials, and a different number comes out. But the problem in machine learning is that we've got a DJ deck, but we've lost the manual. And we don't know what any of the knobs and dials do. Everything's been rubbed out, there's no instructions. But what we do have is data or music to put on one end. And we know the answers that we want to get on the other side. We know what kind of sounds we want to make, or we know what kind of effect we want to have. Do we want people to dance, to jump, or to just casually sway in the streets? So this is what we're going to do. We're going to learn a function by putting data in one side and then playing with the knobs and dials. If you know this comic, you know the ref. Otherwise, we're going to skip very quickly. Now, for the AI kind of thing, my take on this recently, there's a lot of history to the word AI, but I think that people are very keen to use the word AI for any kind of task or technology that they find surprising. If you didn't think a computer could do this task like 5 years ago, then it feels like AI. But there are aspects of machine learning that we take for granted today that used to be the stuff of fiction. And I think a very good example of this is computer vision. So computer vision started getting really good in the late 80s, mid to late 90s. This is an original LeCun. LeCun is the father of convolutional neural networks. And the reason this looks so vintage is because I found it on his website, and I believe that's from 1998. So that's how his LeNet 5 convolutional neural network works. And a CNN is basically a bunch of filters. That's the convolutions. So you can see the numbers after the first filtering look a little bit different, but still recognizable. And then I can't really tell, and then it's completely abstract to us humans. But that's what the computers can understand. So CNNs got a bit good. They could register digits and recognize handwriting, but then there was a bit of a lull. So how did it go from fiction to kind of niche to something that we know is ubiquitous? Well, in 2010, there was this competition that started. A bunch of people put together a data set of 1.2 million images, labeled images, and they were like, okay, take the images, make your models, try and beat the humans. Within a year, we had the first superhuman performance, and in 2012, we had the famous AlexNet, which won by such a margin that it basically propelled the deep learning revolution forward. The net had 60 million of these knobs and dials in the function. 60,000, sorry. And AlexNet has 60 million. So that's the big difference here, is that people realize if I make my thing bigger, it will be better. The reason I point out Facebook here is for the AI lab that they created. So when AlexNet and the deep revolution began, loads of tech giants started hopping on the machine learning trend. At the time, it was still called machine learning because artificial intelligence is something that only the cuckoos were using as a word. It's something that was very popular in the 20th century, and then people over-promised, under-delivered, and so no one was calling it artificial intelligence, except these guys in 2013. I think they reclaimed the word, and that's why we're talking about AI today. So anyways, things got good because there was a method that was developed in the 90s, and then we had access to data. By the 2010s, people had phones with cameras in their pockets and were publishing the data everywhere. And then we had the compute. GPUs were becoming a lot more available because of the CGR industry. These GPUs are what you need to do machine learning maths. So to get a machine learning breakthrough, you need stats, data, and compute. Now, to go back to the astronomy, what that meant, in a historical point of view, is that by the late 2010s, we could easily teach computers to classify images using maths, which is very convenient because most of what we look at are images. So once again, let's spot the difference. Here we've got a before. Most of these blobs are stars. This blob in the middle, beep, that's a galaxy. And then in the after picture, we can see the galaxy again. Oh, this is completely unaligned, but there's an extra blob there. Now, it might be hard to spot, so I'm going to remove the before from the after, and there you can spot it. That's a supernova explosion. That's the kind of job that we have to do every night with our sky survey. The problem is that difference imaging, this exercise of doing one minus the other, is very prone to error, very prone to issues, and you can see we've got difference images with massive, massive artifacts. The problem is, in one night, we get about 10 to 20 million of these difference images that we need to assess, but only a handful of these cool things. I did the math, and I think it would take between 6 months and a year for a single person, if they didn't sleep, didn't eat, didn't go to the loo, to analyze the data for one night. So we have to automate very urgently. So people started automation of these sky surveys, not with AI. That's never where you start. When you need to automate something, you find the dumbest thing that starts to work. You start easy. So the basic cuts are simple. If you see the difference flash in in 4 of the 4 images you can see in one night, it's probably good. 3, it's probably good. 2 or 1, you skip it. That's fine. Then you do the next smart thing, which is you look at the things you know should move or should change in the night sky. So for example, Betelgeuse. It's a variable star. We don't want to find it every night in our stream of data. So we remove those. And once you've done that, you've done a good piece of the job, but you're still left with thousands to tens of thousands of images, which is still completely intractable for a person. So that's why we use a CNN. We use a good old CNN, very similar to the one that Jan LeCun was using for the handwritten digits. So we take the center of the difference image, put it through the CNN, and that gives it a score between 0 and 1. 0 is bogus, it's a technical term, and 1 is real. Now we decide of a threshold where we're going to bin everything below. For us, it's 0.2. If it has a score of 0.2 or below, it goes to the bin. If it's greater, then someone will look at it. Or at least That's the way it used to work. The problem is if you do this, you're still left with hundreds of images a day. People were looking at between 200 and 400 alerts every day, which is tractable, it's doable, so people were doing it, but it's a massive waste of time and it's very tedious because most of these alerts are still bad. And even in the ones that are good, so that's the kind of classification they would do, bad stuff, and then, okay, this is real, but I don't really care about it because it's in the galaxy, and then, okay, this is real, and it's not in the galaxy, so yes, I care about it. So that's the kind of classification people were doing. And when I say people, I'm an eyeballer, so I had to do it too. So, why is it so difficult to automate the next task? Here is why eyeballing is so tricky. Eyeballing is a task that requires different kinds of data to come together. So yes, we have our stamps, our different images happening here, but we also have the scatter on the sky, how wobbly things look. We've got some contextual information, what kind of blob was nearby, was it a galaxy, was it a star? We've got the location on the sky, which does matter, and finally we have the light curve. And the light curve is supposed to be a time series. Here we have one night where we actually see the thing, and then a whole bunch of non-detections. So it was observed that patch of sky, but it wasn't there. These kinds of time series are very difficult to deal with. Most of it, I've looked a lot at time series tools, and the statisticians are very optimistic about what time series look like in real life. My time series do not have consistent spacing. They've got a bunch of weird non-detections or limits. They've got a bunch of weird errors. And in some cases, there's only one point, hardly a series. The other problem is humans are really good at making the most of incomplete data, of using their knowledge and their expertise to actually make sense of this. And so humans are able to do classification. So this is days after entering the eyeball list, and this is how quickly people make the decisions. For every category, they make 99% of the decisions within 2 days. The cadence of Atlas is 1 to 2 days. So they make most of the decisions with just one data point. So that was the tricky thing to automate, and that's why it took so long. But I'm going to spoil the end a little bit. I did it, it works. We have a virtual eyeballer now. The virtual eyeballer is called Stephen, because that is my boss's name, and that is my boss's picture with laser eyes, which he has approved by noticing and never mentioning it ever. It's fine. It's been like this since August because it works. And so Stephen goes on Slack and tells people, yo, the ingest is complete. You have to look at 4 potential extragalactic sources and 4 potential galactic candidates. Stephen does 80% of the work of the eyeballers by basically binning the bad 80% of the bottom of the list. This was a very good week. So every week I've got another bot which sends a report. And Stephen does something very simple. It takes the information, it ranks it, it dumps the bottom of the list, and that's how you go from hundreds of things to look at every day to a few dozen on a bad day. So how does it work? Well, you score your alerts on 2 axes. Does it look real? Does it look galactic? So the colors are the same as we were using before. The stuff we care about is in blue, so it is in that corner of real and not galactic. How do you do this? You learn a function, like I've said before. And that function is learned through something called gradient boosting. If you know what it is, great, we can talk about it, and your favorite type of gradient boosting algorithm. If you don't know what it is, the gist is simple. You start with a very bad guess, and then you make a small function to make it a slightly less bad guess, and then you make another function, another function, another function. And let's take a look at how it works in action. You start with very bad guesses, and then as you add more and more functions, you can see that the stuff we care about nicely pulls in that corner of a plot where we want them to be. So that's all well and good, but how do you turn this into a rank? We're going to use the newfangled technology the Pythagoras theorem. We're going to rank by saying, this is my favorite object. How far from my favorite object are you? And that's it. And with this technique, you can also define a metric called the recall at rank k. And the reason I'm talking to you about metrics and show you a really ugly plot is because it is crucial when you do machine learning, I mean in general, but especially in science, to choose metrics that make sense for the question you're asking. Me telling you how accurate or how high the F1 score is cool, but meaningless to me. What I'm trying to do is order the list, which is, this is the top of the list, this is the bottom of the list, and I want to find as many of the stuff I care about as early in the list as possible. So here we also have another really important thing, a benchmark. This is the curve, boop, the white stuff. This is the curve if you order your list by a number we already had, which is the number between 0 and 1 that the CNN gives, that the previous step gives you. The problem if you do this is that to reach 99% recall, 99% retrieval of the stuff you care about, you have to go down 2/3 of the bottom of the list. And then you're still not sure to find some of the last bits. But with the VRA, you get there in like, oh my God, completely the wrong way. Well, you can see it. 7% to 20%, depending on how early you catch it. So it works, and it works by combining two methods, one from 2017 and one from 4,000 years ago. And so the point I'm trying to make here is that new advances in science and in astronomy are really the partnership between people and the right technologies. And these technologies don't have to be new to be right. If it works, just use it. 5 minutes, brilliant. Agents. I don't know if you've been on LinkedIn recently, or if you're on the AI sphere of LinkedIn, and it's a bunch of people trying to tell you that AI agents are going to take over the workforce, which they probably will, and we should worry about this. But for science, we need to be very careful about where we apply the next level of automation. More to the point, we need to be very careful where we delegate decisions, because the data that we create today is going to be our legacy for the PhD students of tomorrow. So why do we need to be very careful with that newfangled technology? This is a small portion of an image I also took with that phone that took that beautiful picture of the Milky Way. This is a portion of an announcement board at an airport where I was stuck for 7 hours, and I did not want to get up to read the board. So I took a picture with my phone and I zoomed in, and I was greeted by wingdings on LSD, and I could not read the information I was looking for. So why does that happen? Because of something, we're going to skip this, that Neil Lawrence calls Sidolian voids, because of Lee Sedol. You can Google him later. And essentially, what happens is when you have these functions and you're learning how changing and tuning these parameters work, it's a little bit like exploring a landscape. And this is a picture of Civilization 5, where the landscape that you've not explored yet is under the fog of war. So as you explore more how these functions change with different parameters, you uncover the fog of war, and your model is well behaved. The problem is, the bigger your model, the bigger the landscape. And the bigger the landscape, the more you can't explore the whole thing, and the more of these Sidolian voids there are. So for most applications, it's not a big deal, because most applications, I mean, if you're asking for a Google search, ChatGPT does that all day, every day, it works. The problem for me is that, oh yes, and the reason I'm pointing this out is that this, I believe, is why, and the reason I say I believe is I don't work at Google, so I don't know what's in my phone, but I think that's why it messed up my image. Because this phone that did such a good job at cleaning up my picture of the Milky Way messed this up because the software is made to make landscapes and faces and stuff like this more beautiful. In landscapes and faces, you don't have tiny detail that have straight lines and right angles, right? The straight lines and the right angles are going to be the pixels in your image, the stuff that the software is trying to erase. And so in doing this, maybe the picture of the announcement board was prettier, but it destroyed the one piece of information that I was looking for in that moment. And so for me, as someone who cares about the weird and the rare objects of the universe, I have to be so careful about this notion of Sidolian voids. And that's not just true of LMs and agents, it's true of any statistical model. It's just that the bigger the model, the harder it is to explore, and therefore the itchier I get. The other thing with Gen AI is that they are probabilistic models, which you can deal with probabilistic models, and we often do in astronomy, but the problem is you can't deal with it if you don't know the distribution or if you can't track it, which we can't. And finally, LLMs are not trained to be truthful. I really can't emphasize this enough. They do not care about the truth. It doesn't mean they're not right. If they are right, they don't care about it. If they're not right, they don't care about it. This is essential if we are going to delegate decisions to them. And these last two problems are a particular challenge to reproducibility, which is a foundation of science. If we're not doing reproducible stuff, we might as well be doing astrology. No hate to the astrology community. They do what they want. So this is a cool paper that came out really recently that I wanted to highlight about how we use LLMs, because often people see that there's this chain of thought thing happening in the LLMs, and they're like, oh, it makes it more reproducible. It doesn't. It sounds like I hate LLMs. I use ChatGPT all day, every day to help me code, and I'm so much faster with it, but we have to be very cautious how we employ them. So the final reason I want to go back to this is to emphasize that, once again, discovery is a partnership between people and the right technology. Just because it's new does not mean it's right. We are scientists. We have to be as skeptical as we are passionate. Oh, yeah, next slide. Yeah, oh, this is a good slide. I forgot it was there. New technology is an opportunity for new discovery. It's not an inevitability. We have to be as skeptical as we are passionate. We have to try the tools and see if they work. And we have to allow them to fail. Otherwise it's just marketing. So yeah, we should do AI literacy first and AI development second. And I'm going to go to the thank you slide and stop it here. Thank you.